Good morning or good evening, depending on where you're joining us from. Welcome to the first session of our new webinar series on dynamic simulation for the fluid power industry. My name is Simone Serafini, and I did the marketing and communication for VIS Hydraulics and SmartFluidPower. Across these 5 practical sections, we show hands-on how lumped parameter dynamic simulation can support the design and the optimization of hydraulics components and systems, from engineering to test bench, and all the way to energy efficiency improvements. Today, we'll start with a real practical case, building and parameterizing a hydraulic valve model in a real time. Then checking its functionality, dynamic behavior, and performance. Guiding us through the complete workflow, starting from the component drawing, is Giovanni Cillo, co-founder of SmartFluidPower. Giovanni will run a live modeling demo of the CVC.S08 check valve after the company introduction. Please feel free to leave your questions in the Q&A or chat, and we'll get back to you with answer afterward. Giovanni, over to you. Enjoy you all this session.
Good afternoon, everyone. I am Giovanni Cillo, and I am one of the founders and directors of SmartFluidPower. SmartFluidPower is an innovative SME founded in 2018 as a spin-off of the University of Modena, Reggio Emilia. The company currently consists of 7 partners, all coming from the fluid power field with backgrounds in academia, research, and industry. As you can see, our customers all belong to the fluid power sector. We mainly operate in hydraulics, but more generally in pressurized fluid systems, including fuel, water, and similar applications. We focus on virtual simulation. A virtual model reproduces the behavior of a system or a component and helps to reduce the number of physical prototypes and experimental tests. In addition to reducing the physical prototypes, it allows testing many designs directly on computer without building anything physically. This is useful both in the prototyping phase and in the design activities. It also enables fast optimization of an already developed design, reducing time and costs and improving time to market. What are our strengths? Our main strengths are based on the use of Modelica language within an open source environment designed for multi-domain systems. This environment promotes co-simulation through model exchange using the FMI standard. We adopt a block-based modeling approach, which is fast and intuitive, based on lumped parameter approach. SmartFluidPower provides custom services dedicated to the software integration into the company processes, and as I said, our team is completely specialized in fluid power. So the main tools are open source, an open source software that is OpenModelica. It is an environment for dynamic simulation of multi-domain systems that promotes the co-simulation through the FMI standard, and our library that is written in Modelica code and is specialized for the fluid power sector with a lumped parameter approach. For those who are familiar with simulation, this simulation differs from the distributed parameter approaches such as CFD or FEM, which may be steady state or fatigue-based. And our approach is based on lumped parameters, meaning that spatial effects are approximated while system dynamics are fully captured over time. So it is a 0D simulation, or basically 1D simulation. We have developed several libraries: an hydraulic library for modeling complex circuits with valves, pipes, orifices, cylinders, pumps, motors; a mechanical library divided in translational and rotational elements, so masses, sources, sensors; a component library that is used for detailed modeling of elements such as poppets, spools, leaks; and a signal library containing blocks used to provide inputs to our system; and a fluid package that is used to define the properties of nearly incompressible flow. In addition, we provide the development of customized libraries, models, and user interfaces that are tools to use models outside the modelic environment. We also have consulting activities, including the CFD analysis for the models calibration. And we have also training and support. Our case study is the CVC.S08, that is a check valve coming from the VIS Hydraulics catalog. It is mounted in a SI cavity, SI 8 cavity, and this is a section of the valve with some geometrical parameters, and we will perform the simulation with an isobougie oil at 45 degrees. Okay, let's start to model this component.
Yeah.
Okay. Share my screen again.
Yeah.
Okay. Okay, let's start from the mechanical part of this valve. So we will put in our diagram the poppet, the conical poppet of this valve. Okay. That is this component here. Then we will use a piston to set the pressure, the force due to the pressure of fluid. And we are modeling this component here. Then there is also a leakage between the poppet and the sleeve, and its sleeve. So here is the leakage. Okay, and also another piston to close this mechanical chain. Okay, that is this area here, and then we have to insert a translational math to compute the inertia of the poppet and also the spring. Then to close this mechanical chain, we can insert a zero speed here, that is a mechanical end stop of this component, and a zero force. That means that under the spool there are no forces, there are no mechanical forces, but there are fluid forces, pressure fluid forces. Okay, to set the hydraulic part of the valve, we can start from the orifices. The first orifice can be the one of the cavity. Okay, and there is also this orifice of 7.2 millimeter, but in this case it is included in the poppet component. So the orifice of the side cavity is just the one in part 1. Then a volume, that is the fluid between a capacity between the resistance, the orifice, and the other component. And then also on the other port, because here, if you the symbol has port 1 here and port 2 here. So the second orifice is an equivalent orifice for port 2. This is the orifice for the cavity in port 2. Then again, a capacity, a volume P2, port 2. And then also an equivalent orifice that models the 4 orifices of the sleeves, these 4 orifices. So you can use another equivalent orifice, for example, or a sleeve. Okay. And then we have to set the inside part of this valve. Here there is a capacity, another capacity, another volume that is connected to the output of the poppet, to the input of this piston here, and also to this other small orifice that connects this volume to the inside chamber of this valve. So we have a volume with 4 ports, for example, valve. That connects this one to the exit here. And also there is the connection to the one part of the leakage here. Okay. So we need another node to duplicate the ports. Here. And then again, an orifice, that is the orifice of the poppet. It is this orifice, this case, this one, that connects the spring chamber to the outside of the valve. And then again, a volume capacity for spring, for example, to close all the ports. Okay, now we need to test this valve to see its functionality, and also to simulate the pressure flow characteristic. So we can insert a simplified test bed, and for this test bed we will use a ramp of flow rate. That just to simplify the organization, we can use a motor with a variable number of with RPM, variable RPM, and a fixed displacement pump that is here. Okay. Input of motor is a signal. One RPM. Okay, and then we can insert a safety relief valve upstream this upstream the CVC. So, for example, a relief valve is here. And we can imagine that a pipe connects this test bed. That is a long pipe with a certain length, can connect this test bed to the input of this valve. So we can use a pipe. Okay. And then some nodes to connect all the ports. Okay. Okay, and then also we need some tanks for the pump and relief valve. And also one last tank for the output of this valve, to connect to the port. Okay. And last, the block that models the fluid that we will set later. Okay, this is the end of the first phase of the modeling of this component. Then we will start with the parameterization. Let's start again from the mechanical part of the valve. Poppet. Let's start from the poppet. Here we can set the poppet diameter. This 7.5 in this case. The whole diameter that is 7.2. Rod 4.8, and in this case it is a truncated valve with an half angle that is 45 degrees. There is one non-geometrical parameter that is the flow forces coefficient. For this parameter, we will set a parameter in the code that we will calibrate later. So, for example, flow and then we'll declare this parameter. This real parameter here, starting from the standard value of 1. Flow forces coefficient. Okay. Let's continue with the pistons. Piston diameter here is 10.8. It is this value. Then the rod is 7.5 because it is this one value. And then leakage. Leakage, the external value is 10.8 again. The clearance is 0.03. And then also this length is decreasing with the increasing stroke. This is the length of this clearance, of this leakage. This length is decreasing when the stroke, the displacement of the poppet is increasing. So we insert decrease with X, and then the contact length of 9.2. Okay, piston, it is in the opposite direction, and then it is again 10.8. Let's continue with the mass. Mass is 7 grams. Let's also insert a small viscous coefficient that can be, for example, the forces between the poppet and its sleeve, and then also the end stops, starting from 0, low limit, and then the high limit is 3.5. Okay, spring. We know that the spring rate is 12.7, while the preload, here we need a value in Newton, a force in Newton. So let's insert again a cracking pressure that we will evaluate. Okay, okay, the crack is okay. And then we will insert this parameter here. Yeah. Okay. It is 7 bar. Pressure. And to convert this value in force, we will multiply this value for the area of the valve. multiplied by the area, everything in Newton, divided by 4. Okay. Okay, then let's continue with the hydraulic part of this valve. The orifice that models the input cavity, the input orifice in cavity, it is from the side 8 cavities, 10 millimeters. Then again, the orifice in port 2 is 8.5 here, and then the equivalent orifice for the sleeve, and these are 4 orifices of 5.5 millimeters. Okay, let's also insert the orifice here that connects this volume here to the input chamber, the inside chamber of the valve. So this orifice is 2.5, so one orifice 2.5, and then this volume. This volume is just calculated this value. It is about 1 cubic centimeter, and this volume can be important, for example, in a dynamic response of the valve. In this case, it is okay, a check valve, but this can be important, for example, for rapid movements of the poppet. Okay, and the test bed, the RPM, it starts from 0 to 1000 in 10 seconds, so it is a slow ramp of flow rate. Just to have a 50 liters per minute of flow rate, we will insert 50 cubic centimeter for the pump displacement, and then the safety relief valve, for example, at 300. Okay, this pipe can be, for example, at 30 millimeters inside and length of 1 meter. Okay. And the fluid, last thing is the fluid. We can choose the ISO G fluid 46 at 45 degrees. This is an isothermal simulation. Okay. Let's do this simulation. 10 seconds. The interval, it is the number of intervals that are so 1000. And then we start with the simulation. Okay, let's see if let's see before the animation. So the animation is just an indication of how the fluids is moving inside this simple circuits. You can see the pump that is giving a flow rating input, the pressure that is increasing in the chamber inside the valve, also where the fluid is going inside the valve, and also that the mass is moving. If we want to see the plot of the mass, the poppet displacement, this is an example. This is the simulated displacement. If we want to see also the pressure flow characteristic, we can plot for example, in P1, the flow rate and pressure. So let's just improve the plot. Simulation titles. So in left axis is pressure bar, and here is flow rate in theta. And then let's exclude the negative part of the x-axis, and also, okay, this is the pressure drop, the flow rate, the pressure flow characteristic of this valve. And let's compare this this curve with the catalog one. So if we compare this one with the catalog, let's just increase this is so experimental results. You can see that there is a difference, but we here in our model we have just one, in this case, one parameter that is not geometric, that is the flow forces coefficient. We have set 1 as a standard value for this coefficient, but we can try to increase a little bit this coefficient. This value can be also 1.2. I think it's okay. Here you can see that in there is an error. There is a difference between the simulated curve and the experimental one, but the error is at its maximum. It can be 0.5 bar at with a pressure difference of 9 bar. Okay, so it is less than 10% of error. Also, we can not that we have calibrated our model, so the calibrated flow force is 1.2. Now we can close this component, and the model can be converted in a reusable component. So the first step is to create a new model. Let's take everything here, the code, and then let's delete everything that is not our valve. To make this model communicate with the external environment, we will set 2 ports, port 1 and port 2. We can also use an image, for example, just to remember what valve is. Okay. A closed model can also have in its documentation, for example, model of okay. So it can be also quite more complete, this documentation. And then let's draw an icon. I will take the drawing of check valve in our library. This drawing here, and then I will move the ports. Okay. Also, I can set the local name that this component will have in our models, and also it's important, the cracking pressure. Okay, so our component is closed. We can also this parameter, for example, is is a calibrated parameter. So we can, for example, move this one in another part of our interface. So this is just a way to hide this component. Okay, let's substitute this model in our test bed with our reusable model, this one. Okay. So you can see here we have the model that we have just closed. We also have the cracking pressure set inside this model. This is the local name of this model, and also here there is an interface where we can set the cracking pressure and also the flow forces coefficient that is in this case calibrated. So the advanced tab is just another position of this parameter. So let's start again with the simulation. And then we can see in this new that all the components are grouped in this CVC model. Here we can see also the mass is the same, also and we can set again we can modify the cracking pressure. If we plot the, for example, pressure in time, we can change this preload, and the preload is moving here. Preload here is moving at 9 bar. So the curve is translated. This is moved starting from 9 bar. Okay, we can also test this valve in other ways. For example, testing the overshoot of this component. Putting here, for example, an on-off valve, and so giving in input a step of flow rate. So to conclude, this approach allows an accurate prediction of the valve behavior, a reduction of experimental effort if we are redesigning this component, or if this is a new prototype, and also a detailed understanding of the internal dynamics. And this model can be calibrated using experimental data and reused across different systems, different applications. Okay, thank you for your attention.
Thank you, Giovanni. Great discussion. Let's reactivate our camera. Okay. Anyone who registered, including those who couldn't attend, will receive the slide and the recording shortly. As you have seen, building a detailed model of a real component and checking its performance can be fast and straightforward, and it can save significant time later during design iterations and system-level simulations. Now, feel free to post any questions in the chat, reach out to SmartFluidPower privately or via our website or LinkedIn, or include them in the short end of a webinar questionnaire I shared in the chat. Your feedback is important and help us to understand how SmartFluidPower can best support companies in integrating simulation into their processes and making design decisions easier and more reliable. As a thank you, the questionnaire will also give you access to the model built in today's live session, the SmartFluidPower trial library, and a technical consultation tailored to your case. If you're watching this recording on demand, you can still complete it. Will be sent out to you by email, and you receive the same materials. So in the next sessions on April 8, we step up from a single component to a complete hydraulic system and analyze its dynamic behavior across the full operating cycle. If we have some questions, we have some minutes left. Or we can... Okay. No questions for now. Thank you all again for joining this first webinar, and we hope to see you at the next one. Have you all a good continuation. Okay. Maybe we have one. There is one question. Can you tell us about the boundaries of the simulation?
For the boundaries, I think you mean the solver of the in OpenModelica. Because the boundaries, it means the solver, because solver is a DASSL, a standard solver for this kind of problems. It is it is standard in OpenModelica. The tolerance is 1E-6 standard, and and also there are the other boundaries. I don't know if you mean also the operating cycle. The operating cycle in this case is not very simple. It is just a slow ramp of flow rate, and the fluid is oil at 45 degrees. So this is these are the boundary conditions. I don't know if it answers to your question.
Okay. Maybe we came back to you, Alexander, with a response or to discuss our case. Boundaries for dynamics. Yeah, you see it.
Okay, the accuracy. The accuracy is set here. I can show you the accuracy. This one. Okay.
Okay.
Okay. Yes. This is the tolerance of our simulation here. The accuracy, it depends on your the accuracy. I showed the accuracy of compared to the test bed curve. In this case, the accuracy, it was if this is experimental. This is the simulated. This is the experimental curve, and this is the 7-bar. So if we want to calculate the accuracy compared to the experimental curve, we can export the data and then just compare it point by point. But in general, it is I just showed the maximum accuracy that it is lower than 10%, more or less. But if we can compare the accuracy step by step, point by point in each point of this curve. They also have a different If you see the catalog curve is less points to plot, while simulated curve has many points. So also this is a difference.
Okay. Okay.
Transient simulation lacks virtual reality is much higher. Okay, the transient okay are very difficult to simulate, but in general they strongly depends on how your system is damped. So the simulations are much influenced by the capacities inside the system. So of the volumes of oil that are inside the chambers, for example, or all the chambers that I have not set here are the chambers of volumes of oil in this component. They influence the transient response of the simulations, and also the inputs. If we have, for example, a valve that is opening with a step in how much time it is opening, also this influence the. But the most is the damping by the fluid. Also, how much air is in the fluid, the incompressible, the bulk modulus of the fluid. So there are many parameters that can influence the transient response. So if you know them, but you also maybe have to consider the trend of your results more than the specific number. Experience, yes. In our case, the model is the fluid model also includes a sort of simulation of the cavitation, for example. In this model, we can also insert the percentage of air in fluids. For example, here we can set the here the percentage, and we can set, for example, this is standard 0.1%. Also, we can set the saturation pressure. In our case, the cavitation that is we work at 0 bar as a relative value for the pressure. So what is under 0 bar until -1 changes. It is not a simulated cavitation, a detailed cavitation, but it's just it modifies the parameters, for example, the bulk modulus of the fluid, just to simulate the presence of the air in fluid. So it is not a CFD simulation. It is just it just modifies some parameters according to the percentage of air that is free in the fluid.
Okay.
Okay.
Okay. Thank you for your questions, and hope you all to see the next webinar in which we will simulate an entire hydraulic systems on 8th of April. Have a good continuation.
Bye. Goodbye.
Goodbye.